So I hope you can see, and yeah, hopefully. So we were talking about random variables. Random variables. We discussed about how random variables are generated. So basically, we discussed about how a physical experiment can be uh, can be used to generate the random outcomes, and then those random outcomes will be plotted as random variables. So when we take, for example, we discussed about random experiments such as flipping a coin. So flipping a coin can be considered as a random experiment. So random activity that we are doing. So we don't know exactly the outcome of that experiment, right? Once we are doing that experiment, we can understand the outcome. So let's say the flipping of a coin is a random experiment. The coin can have like either head or tail, and it will, if it is a fair coin, then the output will either be head or tail, depending on that situation. We don't exactly know the output. So because of that, we call these experiments, random experiments, which gives random outputs. So we can have either head or tail. So in that case, if you have heads, you uh, you call that output, um, and you call that output head, and you denote that head as either uh, uh, 0 or 1, let's say. So you can denote the output using a real number. You denote the head as real number. Let's say we denote it as 0, and then that output can be denoted in the real axis. So if I take the real axis values, I can take the general, the general axis that I take as, x. The x can take either 0, or x can take maybe tails, right? If the output of this experiment is tail, then if there's another output and that output is tail, then we can denote that output as 1. So this kind of a um, experiment generates random variables. So the random variable can take 0 or 1. So it can take any real value. So if it is a discrete situation or discrete process, uh, or discrete experiment, then we have discrete outputs, or countable outputs, right? If we have countable outputs from our random experiment, then we call that as discrete. um, uh, we can mathematically denote these outcomes using discrete random variables. If we have uncountable outcomes, then we can denote that using continuous random variables, right? If there are uncountable outcomes from this random experiment, we can denote each of those outcomes through a real number on the real axis. It could be any value. If we take the outcomes are taking a value between 0 and 1, it could be a value between 0 and 1, and any value in between this range can be taken as an outcome. if it is a continuous process, if it is a continuous, I mean, random variable. If it is a continuous random variable, we can consider that any value between this range can be taken as an outcome. Each outcome will be denoted using a number, using a real number. So these real numbers can take any value between, for example, 0 and 1. So it could be 0.1, 0.001, likewise up to any point in between 0 and 1. So we discussed about these continuous random variables and the discrete random variables, and how we can understand, or how we can observe the behavior of these random variables is done through the probability density functions and probability mass functions, right? So we discussed about, like, how we can represent random variables and their behavior, and it was done through the uh, probability density functions and probability mass functions. So probability density functions are used to denote the behavior of a continuous random variable, and if it is a discrete random variable, we use a probability mass function. Probability mass function, if we have a discrete random variable. So these are the things we learned about the random variables. Random variables can be continuous random variables, can be discrete random variables. Continuous means you can't count the number of outcomes, because the number of outcomes can be any value between two fixed limits. It can be any value. We cannot even count. There are infinite amount of outcomes. If it is a discrete random variable, the amount of outcomes are countable. That means that we can count the number of outcomes uh, in that random experiment, and then we can denote those outcomes as discrete random variables. So there are specific numbers that we can use to denote the outcomes of the experiment. Uh, so, apart from that, in order to analyze these random variables, how these random variables, or how these outcomes of these experiments behave, we have we are using the probability density functions, right? If it is a continuous random variable, we are using the probability density function, which we denote as fx. And then if it is a discrete random variable, we use the probability mass function to find the behavior of the random variable. So in order to find the probability of a certain outcome happening, we need to use these probability functions, probability distribution functions. So for both cases, it is like that. So we can denote this probability mass function using, let's say, using the notation p x x. Let's say we are using like that. So we are using a, uh, mass function to find the probability of the outcomes using this function. To find the probability, this function is needed, right? So the importance of the probability density function is that it allows us to find the probability of some kind of a random outcome happening. Okay, so um, uh, that is the importance of these probability density functions and probability mass functions. So in the last class, we went to another step where we discussed about the joint random variables, or I will call them as the multiple random variables. Okay, so if you have any questions, you can ask. So this is for the single random variable case. For the multiple random variable case, the same thing happens. Some certain experiment we can consider, and we can denote that experiment using multiple random variables. So we can denote the uh, outcomes of a random process using two random variables. So the two random variables are used to denote the outcome of a random process or random experiment. So the random experiment outcomes depend on um, two random variables, x and y, let's say. So x and y um, both determine the output of the random experiment. So so the output of the random experiment is defined in another dimension, which so it could be z axis. So if there are if the outcomes can be denoted in the x-axis and the y-axis, then some values we can take some values in the x-axis and we can take some values in the y-axis. Combination of those values will produce this outcome. So the outcome of the random experiment in this case will be a point in the space which is x and y, which is defined by both x and y. So this point is defined by both x and y. So x can take a certain value, y can take a certain value. So once those values are taken, the final uh, final output can be a value in the third dimension, which is denoted by both those x and y variables. So in the last class, we discussed about how we can denote the joint PDF functions and the joint CDF functions, right? So we discussed about two random variables, and when there are two random variables, we discussed about how we can denote the PDF function, how we can denote the CDF functions when there are two random variables in place. So the PDF function, I will say it would be denoted using x and y both. It will be denoted using x and y both. So it will be fxy and inside brackets simple xy. And then for the cumulative distribution, it would be capital XY. Inside brackets, it would be simple XY. So we can plot the specific probability density functions for the multiple random variable case. So we can obtain a certain probability density function and we can plot the related cumulative distribution or cumulative density function. So the density functions are defined for continuous random variables, right? So density functions are defined for continuous random variables. So for the continuous random variables, in order for us to, find the probability, this density is helpful. This density should be integrated to find the probability of a certain continuous random variable. And uh, uh, we have to take the integration to find the probability. So if we want to find the probability of a certain event happening, we need to take the integration over a certain range of x values and y values. So if there are two random variables, we need to consider the ranges of the x range and the y range. We need to consider the ranges of all the random variables that are affecting the outcome to find the probability of the outcome occurring. So that is what we were discussing in the last class. And today, I think we are going to start talking about uh, uh, a next concept about the random variables, and how we can define the parameters, such as the average or the expectation parameter of the multiple random variables, right? So when we consider those things, I think we will move into those things. So since we have already discussed about the joint PDF functions and the joint CDF function, we have also talked about the marginal PDF and CDFs. We have talked about the conditional PDFs and CDFs. So with all that definitions, now we will move towards how we can discuss the other statistical properties of multiple random variables. So basically today we will be focusing on that part. So the statistical properties of the multiple random variables. So when we are looking at random variables, when we are looking at random variables are a denotion, or uh, random variables are a way to define outcomes of a random experiment using real numbers, right? Define outcomes of a random experiment using real values. So random variables are real values, which are used to basically uh, mathematically uh, mathematically present uh, the outcomes of a random experiment. So random variables are real values. These random variables, there are multiple random variables. Uh, we we would like to know how the probability of some event occurring uh, when there's multiple random variables in the random experiment. So the random experiment is affected by uh, the multiple random variables. Random experiment affected by multiple random variables. So, so in the last class, I defined this situation where we have two random variables in place. One random variable could be the time, right? The time in the day. And the another random variable could be the temperature, temperature in the environment. So depending on the time and the temperature, we can measure the probability of uh, of being able to sell certain item, right? We can denote the probability of being able to sell certain item. Let's say it's actually financial thing, but we can count a probability of some kind of event occurring. So we'll say we are going to sell some item. So ability to sell some items. So sell some items. It could be some food. The probability of selling the items will depend on both the time random variable and the temperature random variable, right? So the time can take any value between certain uh, time, right? From 6 a.m. to 8 p.m. And then temperature can take any value between the normal environmental temperature ranges. So depending on these two factors, the probability of selling the item will change. So if we have the function of selling the item, then we know, like we can find the probability of an item getting sold during a certain time duration and when there's a certain temperature range, right? So this is one of the examples where we have multiple random variables, right? So these multiple random variables combine together to generate a certain outcome in the in the in the random experiment, and that generated outcome has a certain probability, and that probability we can denote using probability density functions, and that probability density function can be used to find probabilities of the event occurring. So the PDF, CDF, those things are useful for that. Apart from that, another important property uh, of this kind of experiment is that the average, or we denote the average in statistics using the expectation operation. So I will call this as average, right? Average or average, I think you all know what average is, right? Once we have a number of data points, we take the sum of all the data points and divide by the number of data to find the average, right? So once we have, let's say, I I equals 1 to n data points, we divide by the n number of data points, and we using that we find the average of the data points. Just like that, in this random process analysis, or in this analysis where we try to find the probability of a certain outcome occurring, we find the expectation of the random experiment. So in order for us to find the expectation means the average value. Expectation means the average value. It is denoted using this uh, uh, this integration, just like the single random variable case. For the single random case, for the single random variable case, we denoted or we defined the expectation operation of a single random variable x using this function, where we find the average of the random variable by taking the random variable and taking the product with its PDF function, its probability density function, and taking the integration of that over the range of the x values. So whatever the range of the x values we consider, we take the range, we take the total, probability of the values, the probabilities we compute um, that occur during that x range, and then we take the integration, and by doing so, we can find the average value of the random variable. So average value of the random variable gives us an idea about what is the average average value of the random variable which occurs the most. So the random variable value which has the uh, most probability of occurring. So if we take a Gaussian random variable, we have the random variable. If we have the random variable x, so if we have a Gaussian distribution as the probability density function, then the probability of x around its mean or its average will be the highest. The mean value will be at the middle of the distribution. So at the middle of the distribution, the probability of a certain event occurring is the highest. Then what we trying to find is this middle point at which this highest probability is occurring. So by finding this expectation of the random variable, we can find the point of the random variables, uh, and we can find from that point, okay, this is the random variable value which occurs the most. This is the random variable value which occurs the most, or this is the outcome of the experiment that occurs the most. Likewise, we can find the expectation. From that expectation, we can get some idea about the outcome which occurs the most in the random experiment. So for the single random variable case, this is the expectation operation. For the multiple random case, we can define the expectation operation with the two random variables. The expectation with two random variables, we can denote using this integration, same as before. In here we have two double integrals, and in here the x and y could be having certain relationship between the x and y variables. Therefore, we will put the x and y uh, uh, variables as a function of x and y. Then we take the multiplication with its probability density function xy, and then we integrate over both dx and dy, right? So uh, that would be uh, kind of the general description of the multiple random variables probability density function. Do you have any questions so far?
No, ma'am. Thank you.
Right. So for the other parameters also we will get into. So we have the covariance function and the correlation function that we are going to talk about uh, after this regarding the multiple random variable case. So for the expectation, this would be the function, and for other parameters we will talk about, it would be regarding the covariance between two random variables x and y. For the covariance, we are going to be discussing about um, the variance uh, variance between the two random variables. It is defined as the expectation of x minus mu x and y minus mu y. This is the definition. So this can be further elaborated using this integration, where I take the integration over minus infinity to plus infinity for both x and y random variables, and take the integration with respect to the PDF. I mean, I take the integration with the PDF. So the integration will look like this: y minus mu y, and then I take the product with the joint PDF function, and then I take the integration like this. So what you need to understand is that once you add the expectation operation you need to include the function inside the expectation operation, or um, the function that uh, you are trying to find the expectation of. You need to put inside, include in here, as the function, or as the as the function that you will be integrating uh, with the probability density function. So this is the probability density function. So you will be taking the product between the this is the kind of the gxy function that we talked about is earlier, and then we take the product with the PDF function, and then by doing the product, then we can find the covariance value, right? So I will now I would like to give a small uh, like kind of uh, give a small activity for you to do. I want you to find the covariance value with respect to the covariance value using the expectation values of the x and y, right? I want you to find this final value using expectation values of, you can use expectation values of x, y, expectation value of x, and expectation value of y. If possible, you can try to find the final answer for this by solving this integration. And then you can try to find the answer to this covariance using these expressions, EXY, EX, and EY. So I hope you will try to do that. So in the meantime, I will also explain to you, after giving you some time, I will explain to you how to obtain the result. Right? Can you try to take the integration, and then can you try to find the output in terms of EXY, EX, and EY?
Yep, will do.
Okay,
I'm
thank you.
sure we can do it, Zora.
Okay, maybe you can try. We will then get to it. So this is the mu x, this is the mu y. So in this earlier definition, I would rewrite it as EGXY for any general case. To denote any general case, I will put this as EGXY, because once I put EGXY, I know that whatever the function that I define inside this expectation operation should come into this integration in the same form. And I can do the rest of the integration process with the PDF function. So I will take the product with the PDF, and I will take the integration. So I will start explaining in 1 minute. Regarding the integral, I will explain. Okay, I think I will get to it. So we need to actually first find the so I mean we need to multiply these sorry, we need to multiply these two brackets first. So you will get xy minus mu xy plus, sorry, minus mu yx minus mu yx plus mu x mu y, right? So I hope you got to that point. I will put this as real number. And then I also want to take the multiplications now. When I take the multiplications, first will be, I will be taking them separately. And the xy into fxy would be, sorry, I will write it in this manner where you will denote the f. In here it should be capital XY, right? In here it should be capital XY. We will go with the notations. So capital XY and inside bracket simple XY, and then you take the double integration with respect to dx and dy. So what is this? From our definitions, what is this in terms of expectation operation?
That would be EXY.
Yeah, exy, right?
Yep.
Yeah, it's correct. So exy. Then I am left with the next components. So double integral mu x is a constant, right? Mu x is a constant here. So it's a constant. It's a average value, some kind of average value of, I mean, mu x is the average value of x variable, mu y is the average value of y variable.
Is it EXY minus EXEY?
Sorry, xy?
Uh, the answer is it EXY minus EXEY?
Yeah. So,
Thank you.
yeah. So I will now, uh, what you need to do is, I mean, I'm going to do in the integration format. So I can take this as mu x y fxy dx dy, and then comes minus, so yeah, minus mu y x into fxy xy and dx dy. Finally, I will get the plus sign and I will get this expression where mu x mu y will be multiplied with this fxy xy and dx dy. So these mu x mu y are, we can denote them as ex ey, right? And then these are
Yep.
constants. We
Yeah.
can take them out. So what is left afterwards? What is the total value of the other integration?
It's just one.
Yes. So once you take ex ey to the outside, you are left with the integration of a probability density function, right? Probability density function over the total range over with the probability density function is defined, right? So the probability density function over all its values will be equal, the integration of that probability density function over all its values, all its x and y values will be equal to 1, right? It is a rule of the probability density functions, which means that the probability of each outcome, the sum of probability of each outcome will equal to 1, right? I hope it is clear for all of you, right? So because of that, this integration will be equal to this ex ey, because this integration will equal to 1. Therefore, we will be able to cancel out this part, or just assume it is 1. And then we are left with ex and ey. So I will try to erase this part and then represent that only using ex and ey. So now we have the task of dealing with these two integrals. So the first integral that we have to deal with is this mu x y fxy inside brackets simple xy dx dy. So mu x, as we said, is a constant value. So since we are first taking some kind of derivation with respect to, let's say, x, we are taking with respect to x, then so I will try to get that integration up to here. So mu x y fxy xy dx dy. Integration with respect to x first I will consider, and if that is the case, then y, all the y variables will be considered constant, right? So in that case, I will be able to take mu x out because it is a constant, and I will be left with y fxy xy, right? Sorry, I mean, so if I'm taking the integration with respect to x, then all this will be constants. Y value will be a constant. I'm going to take mu x and y out, and I'm going to be left with, and dy also. Dy also, I will consider as a constant. I will be left with fxy, xy, and dx. And I will be left on the outside with this integration with respect to y. That I think I will have to do later, which I will denote. I think I need to put this dy also at the back, but I will deal with that later. First, I need to deal with this integration, which is um, uh, which is uh, yeah, I will be doing the integration with respect to x, and uh, this would be equal to the marginal distribution of y, actually. So in the last class, we discussed about these marginal distributions and their definitions. So I will try to get the definition, right? So it is defined as the integration of the joint distribution over a certain random variable x or y. So the marginal distributions are described using, uh, so this is the marginal distribution of uh, y, because we are changing only the values of x, but we are keeping the value of y constant. This is the marginal distribution of marginal PDF of y. It is a definition. It comes with a definition. So the definition of marginal PDF of y is the integration of the joint function with respect to the dx. A joint function with respect to dx will give, I mean, over its all values. over all its values. So like it could be minus infinity to plus infinity, and like this integration of the joint distribution function over the x values, all the x values, is known as the marginal PDF of y. The reason is that in here we are keeping the value of y fixed at a certain point, and then we are varying the value of x over all the x possible values. So because of that, we call this integration marginal PDF of y. So inside these brackets, what we have is that same expression, marginal PDF of y. So marginal PDF of y, we can input in here. So mu x into y, marginal marginal uh, PDF of y we denote as f by y. In here it's capital Y. And then we take the integration with respect to y. So since mu x is a constant, we are left with fyy y dy integration and mu x. So this expression is basically ey, right? I hope it is clear to you. Expectation operation of a certain random variable is its random variable into its PDF function and its integration. So so I hope it is clear to you. So this is EY. So since this is mu x is EX, we can denote this product as EX EY. So initially we started with this integration and we had this expression, and mu x is actually EX, which we can denote anytime. We can take this out because it's a constant. And once we have it out, then we are left with this other integration, which is purely related to the y variable. And then it can be denoted using EY, because the definition is that once you take the product between y and its PDF function, take the integration, then it will result the expectation operation of that random variable. So these two EX and EY will give will be the final value of this integration section. So similarly, we can follow the same method to find the integration of this third section, which we won't go into detail, but that also will result in giving us output of EX and EY. So I don't want to do that again. Same procedure as the earlier example will follow. The only difference will be that in that we will be considering the marginal PDF of X. So our initial situation was that we wanted to find out the integration values of each of these components. So I will try to erase these or the uh, additional integrations that I have done. So I will come into this level and I'm left alone with this integration. So I have found that this first integration equals to EXY by definition. Then once I solve this expression using my integration separately, I can find it is the product of EX and EY. Thirdly, when I do the integration, it would be EY into EX, because we will be able to take EY first outside, and then I will be able to show that the remaining part equals to EX. And then finally, I'm left alone with EX and EY, which is because we have taken the integration of mu x and mu y with respect to the joint PDF, which gives a value of 1 when we take the integration. And then we will be left alone with this. So when we are taking the product, since these are equal, we can cancel these out. This will be cancelled out. We'll be remaining with this expression. So the covariance of two random variables, x1, y, we denote using expectation operations as given in this expression. Do you have any questions? If you have any questions, you can let me know. So the covariance x and y can be uh, denoted using this. So the covariance is basically an a definition which is used to measure the variance between two random variables x and y. Right, the variance between two random variables x and y we are trying to measure, and that is known as the covariance. Or co means like there are two things happening, two random variables, or one or more random variables. I mean, there are more random variables than one. When we and in that case, we consider covariance. We are not only considering one variable, but there are two variables that we are considering. So we can consider the variance behavior of these two random variables and get an understanding or get a measure of how these two variances are similar, right? So the variance of x could be something. It could be sigma x squared. Variance of y could be something. And we are trying to find how similar those variances are using this expression, right? That is one idea behind the covariance. So you can try to understand that covariance further in your own free time, and also try to get this output on your own in your own free time, this covariance expression. It is one of the results of results that you can maybe try to derive on your own. So covariance between random variables x and y can be denoted as exy minus ex into ey. Right? So this is the kind of the expression of the covariance. So there are other parameters that uh, we can use to study the random variables, multiple random variables. So another random parameter or statistical parameter is the correlation. And this is very important because it comes all the time in all the in most of the places where we are considering about two random variables. So two random variables or two signals, something where we are comparing two signals or two signals, or two random variables, uh, and also 2 points in the same signal, 2 points in the same signal. If we try to study those, we will be talking about the correlation. What is the meaning of correlation? What does it mean? That is the question that I'm trying to explain. So the correlation is the relationship between 2 points, right? How similar those points are, how similar those data points are, right? So correlation is, we can denote that mathematically, and using that mathematical equation or function, we are trying to give a value for the similarity uh, between two signals, right? So between two signals or 2 points in the same signal, right? Between two data points or between 2 points. So similarity between certain points we can find using correlation. And we can denote that mathematically using integrations, and I will explain to you. Just you want to understand that correlation gives us a value of how similar those things are. If the value of this similarity is high, then we know that the signals are very similar to each other. Signals are very similar to each other. This is an indication that the signals are almost same or similar. And if the value of this correlation coefficient is low, then we know that there are two very different signals, right? So we use this correlation function to easily identify that without going through each and every data point in the signal. We can find the correlation value, and if the correlation value is low, we know that the signals are not having much of similarity, they are different. However, if it is high, we know that maybe a very similar signal is occurring in another time instance, or we are comparing two very similar signals. So that is what we are trying to find as correlation, right? So we will get into the definition of correlation. So as I said before, correlation is the similarity between two signals. I mean, I cannot say that exactly that it is a similarity, because like we are in here, basically we are focusing on the linear similarity, right? We will get into that in the next time instance, but we are going to be focusing on whether they are uh, there's a linear similarity between the two signals. There could be nonlinear differences. There could be some other differences between these two signals, but there's some kind of a linear uh, relationship between these two signals. Then we call that the correlation of the two signals is kind of high. So the correlation, the correlation between two signals, right, or multiple random variables, right, between multiple random variables, we define as using, I mean, EXY. We can denote it using EXY, where we denote the correlation between X and Y random variables. Right, using EXY, we denote the correlation that exists between the X and Y random variables. So the correlation between X and Y random variables. So the correlation between these random variables we can find using this integration xy fxy inside brackets simple xy dx and dy. Then we take the integration. So it's going to be double integration because we are having two random variables x and y. We are going to take the integration over the entire real number range. So the correlation can be defined as this integration, where we take the multiplication between the two random variables, and then we take the product with the probability distribution function or probability density function in here. Because we are considering continuous random variables, we are going to consider the probability density function, and then the integration will give us the correlation between the two random variables, right? How correlated those two random variables are. So actually the outcomes of a certain physical random experiment, we can denote using the random variables. So the physical, I mean, the outcomes of a random experiment, if we can denote using X, and the outcomes of the random experiment, if we can denote using another random variable Y, then what is the relationship between the X and Y? So that is denoted using this correlation, and then this integration will give us the correlation between these two random variables uh, that we use to define the outcome of a random experiment. Anyway, so this mathematical integration we need to use to find the correlation, and its value, as I said before, gives a similarity index uh, about the I mean similarity index about the similarity between the two random variables, and later we will consider about the random signals. So it will give us an idea about how two values are similar to each other. In this case, we have another definition related to correlation. The correlation is something that is going to come up all the time. We need to know, different parameters related to correlation. So correlation coefficient is defined as using standard notations. Is defined using rho xy. It gives the correlation coefficient rho xy, and it is defined as the covariance that we discussed earlier, covariance xy divided by the the square root of the variance of x and square root of the variance of y. So this will give us covariance of xy divided by the sigma x and sigma y. So this output will give us the correlation coefficient value or rho xy. So this correlation coefficient value is also used to understand the correlation between x and y random variables or x and y outcomes. So I mean the values of x and y, the relationship between the values of x and y, we try to find using these correlation coefficients. Uh, Another thing is uncorrelatedness, right? We talked about the correlation. Another thing we need to discuss is the uncorrelatedness. Uncorrelatedness. Uncorrelated random variables. So, so we talked that correlated means similarity, right? So uncorrelated means that these random variables are not correlated. They are not similar. There's no relationship between them. Okay, so uh, we define these kind of uncorrelated signals by this feature EXY, and EXY should be equal to EX into EY. So the expectation of XY will equal to the product between EX and EY. The reason is there's no like linear relationship between X and Y random variables. Because of that, we can take the X component separately, Y component separately, and then we can take we can consider the expectation of X component separately, and then we can multiply that with the Y component's expectation. So this relationship is valid for uncorrelated random variables. Uncorrelated, or they are not that much having any kind of a similarity. Because of that, we can consider these X and Y in a kind of a separated manner, and we can consider X separately, Y separately. So uh, that is about the uncorrelatedness, right? So we can denote this using integration also. For uncorrelated signals, uh, we can, using integration, we can show this. So situation where we have the values of X and Y in this integration. In this integration, we can take the integration like this, and then since they are uncorrelated, X and Y, this I mean um, this this integration, in this integration, X and Y are not related. So because of that, this integration can be defined using X separately and Y separately, right? So I think we can go into the previous explanation we had also about the marginal distributions. So where we take the integration with respect to X first, then we uh, since uh, our function is only varying with respect to x, then we consider the marginal distribution. So I will take the integration with respect to x first, and then I will do the integration for y next. So x, y. So I will take y out because x, yeah, y is not related to x. So because of that, I'm taking y out. Then x, fxy, xy. Then with respect to dx, going to take the integration. Uh, So fxy, whatever the function, fxy joint distribution is related to both x and y coordinates, so x and y variables. So we cannot take y. So mm, so the joint distribution function also uh, we need to consider based on the two random variables. So we can consider it has both x and y components in it, and we need to actually consider the two random variables. If they are uncorrelated, there's no relationship between x and y, right? The final integration will be like the integration of x separately uh, as a product with the integration with y separately. So uh, since there's no relationship between this x and y random variables, the this integration we can write as like x behaving separately, y behaving separately. So x integration will, I mean, uh, x will be considered separately and y will be considered separately. So basically fx x will be extracted and it will be used to denote the integration with respect to x, and then y will be y behavior will be uh, extracted, or it can be studied separately, and then it will be integrated separately. So this uh, y and x, they are uncorrelated. Because of that, we can consider behaviors separately, and then we can multiply with their own probability density functions, and we can take the probability with respect to their random variable separately in the integration. So we don't have to consider the relationship between x and y in the joint PDF function. Uh, and in contrast to that, we can consider separately the x behavior, and we can consider the y behavior separately, and we can take the integration as a product. So this will give us the ex and ey product. So the independent, or I mean kind of isolated behavior of x is taken into consideration and y is taken into consideration, and the integration is computed likewise. So do you have any questions? Right? So in the uncorrelated case, you need to consider this as the behavior of uncorrelated random variables. Exy is equal to ex and ey. You have to consider this expression as the behavior of uncorrelated random variables. So if you have any questions, you can put in the chat. In the next, as the next type of random variables, or another property of random variables, is the orthogonal random variables. Orthogonal random variables. So in here, actually, orthogonal random variables um, are basically random variables which do not depend on the other random variable, right? So the property of orthogonal random variables is that exy is equal to 0. That means that for orthogonal random variables, the inner product between the x and y random variables is going to be equal to 0, right? So I will I will try to explain that using yeah. So the definition is that the inner product of the x and y is equal to 0. So the inner product of x and y is going to be equal to 0. So that means that in general, the main meaning of that is that there's no relationship between x and y, and also, I mean, there's no uh, uh, so in the orthogonal case, there is no there's no, what do you call, there's no similarity, and also the inner product is completely 0. That means there's no relationship at all in the orthogonal random variables. So what is the difference between correlated random variables and these orthogonal random variables, you will ask? So in correlated random variables, we have like nonlinear relationship at situations. So in this correlated part that we discussed earlier, the correlation between multiple random variables, in there actually the similarity or linear similarity is 0, but uh, there could be some non-linear similarities. Linear similarity is 0, but there could be some non-linear relationship between these random variables. So because of that, there's some kind of similarity between the random variables when we are considering the correlation, right? We will say that the linear similarity or the linear relationship is 0. However, there could be some other dependencies between these two random variables. However, in cases where there's no dependency, or no dependency between the two random variables, such that these two random variables uh, uh, can like I mean, sorry, there's no um, there's no combination, or there's no there's no interference, I will say, interference between these two. There's no interference between these two random variables. So one thing I would like to explain is that in examples, as example, we have the situation where we transmit different signals in when we are transmitting signals in our wireless communications, we use different frequency bands, right? When we are trying to send some signal, we will use different frequency signals. So we can transmit signals with F1 frequency, and then we can transmit frequency signals with another frequency. So when we are transmitting these two signals at the same time, using FDMA, for example, like frequency division multiple access scheme, then if we have, if we have similarities between these two signals, then the receiver will be, the receiving device of this of these signals of the receiving device which is in a nearby region will receive both these signals, right? If the receiving device wants only to hear the F2 signal, then it needs to cancel out this F1 signal. So in order for us to do that, we need to make sure that F1, F2 product is 0, right? So if F1, F2 product, inner product between the values of this, F1, F2, signals, right? The 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 frequency of these F1, F2 signals must be having an inner product of 0 in order for the signals to um, be like orthogonal, and then the signals to be decoded separately. So in OFDM, for example, and in FDMA as well, we use these orthogonal frequency bands to transmit different messages and transmit the signals to each of the different users. So the frequency bands that we are considering must be like orthogonal with each other. So F1 frequency band should be orthogonal to F2 frequency band, and only then the two signals will be transmitted in such a way such that the signals will be orthogonal, one thing, and that orthogonal thing will make these signals be decoded separately. So if we send orthogonal signals, the receiver will be able to decode the signal separately. So decode the signals easily. If there are some kind of a relationship between these two signals, like if the orthogonality is not there, then there's interference from one signal to the other signal, such that we need to remove that when decoding the signal. So I think we will discuss about that further as well. So orthogonality uh, is defined as mathematically as the case where the random variable's inner product is equal to 0. Then I will uh, discuss about um, another situation, right? Another uh, feature of random variables, multiple random variables, which is the case where uh, the independence of the random variables is considered. So independence or independent random variables. So independence is also another kind of similar concept. And in here, we have uh, the mathematical definition as EXY equal to EX and EY. So again, the same mathematical relation, that we discussed in the correlation section is coming here. The same definition that we had under this correlation section. Right? So uncorrelated section. So in uncorrelated random variables, we discussed that EXY is equal to EX and EY. So in uncorrelated random variables, that means the similarity between the two signals are very low, such that it is like the once we have two random variables, the one variable X is behaving on its own and Y is behaving on its own. And therefore, if we take the product between these two signals, then we need to take the product separately of those two signals, right? So in orthogonal case, once we take the product, it's going to be 0. So the reason is that there's these two random variables are like totally not related at all. They are totally going in two different, they are working in two different dimensions, and that because of that, the behavior of one random variable does not affect the other random variable at all. Because of that, when we take this EXY, the value of that expectation value, the value of this EXY is going to be 0. Because the operation of one X does not affect the other X at other random variable at all. Because of that, the product, or the product means like how, what is the product is the kind of the relationship between the two random variables. So the product is going to be 0 because there's no relationship at all between X and Y random variables. So when we are talking about independent random variables, the same concept of uncorrelatedness applies here. However, the difference between these independent random variables and the uncorrelated random variables is that independent random variables will always be uncorrelated random variables. Independent random variables will always be uncorrelated random variables. However, uncorrelated random variables will not be independent all the time. This does not happen all the time. Sometimes this might not happen. So uncorrelated random variables sometimes might not be independent, which means that in uncorrelated random variables, there could be random variables that have some kind of dependency between its uh, random variables. So the random variables will have some kind of dependencies between them, and if it is there, then those random variables cannot be considered as independent random variables. So because of that, uncorrelated random variables cannot be considered as independent random variables all the time. However, all the time we can consider independent ones will be uncorrelated all the time. So that is basically regarding the independent random variables, uncorrelated random variables, and also about the orthogonal random variables. When we take all of those into one table, we can denote that there are three basic, types of random variables, right? The types of random variables we can denote as independent random variables, then uncorrelated random variables, thirdly, the orthogonal random variable case. So orthogonal random variables. So the properties that we discussed were that EXY equals to EXEY in here, right? Because the independent random variables, the X and Y are working in independent manners. So there's no relationship between them, and because of that, the processes can be evaluated separately. In for uncorrelatedness also similar definition is there. Uncorrelated means ex and ey. However, although it is uncorrelated, sometimes we cannot say it is independent. Uh, we cannot say it is independent all the time, because sometimes if x and y have some kind of relationship between them, non-linear relationship between them, then those x and y will have some kind of dependency, and because of that, we cannot consider them as independent. So that means that x and y are dependent. If the x and y are dependent on each other, then those x and y cannot be considered as independent random variables. In the third case, it is a special case where we have the x and y. Sorry, in here I will remove the comma. Right, it should be the product between the two random variables. So the product between two random variables is going to be 0. So which means that uh, we can we can we do not have any situation where these two random variables will have the inner product equal to 0. The values of the random variables inner product will always stay 0. So which means that um, if so the the situation that we have both x and y occurring at the same time is going to be 0. I mean the same at each point of x and y, at each value of x and y, um, the when we take the product of each for each value of x and y, we will see that the product will equal to 0. So the product, the average of all those products will be equal to 0, right? So we know that multiple random variables have x and y, right? So the final output we can find, um, uh, I mean, we can find the xy products, right? The values of y we can define as, let's say, 1, 2, 3. And then the values of x we can define as maybe another something -1, maybe -2, something like that. So by taking the xy values, if we take the x and y values and take the average of all those x and y values, we will take the xy values, so all the possible xy values, and we take the average of all those possible xy values. And then average values of all those xy combinations will equal to 0 in this situation. That is what happens with the orthogonal random variable case. So we use orthogonal random variables, like it is an important random variable in many applications, and we are using this orthogonality for applications. So applications such as OFDM communication, FDMA communication. So those communications require the knowledge uh, of using orthogonal random variables, uh, such that the the product between the random variables will be 0. And using this concept, we can reduce the interference between two random signals. So anyway, the definition for the orthogonality is EXY equal to 0. So using these concepts, we can actually solve some problems. So one example is that uh, the expectation of a random variable x is going, let's assume it is 3, and expectation of the random variable x squared, let's assume it is 11. And then we have a function such as like y. which is another random variable that is defined using x and that is defined using x and some other real numbers. So now I will ask you to find the expectation of y. Can you find the expectation of y? So expectation of y. Right? I will give you some time. Can you try to do that? I also want to find whether x and y correlated. So if possible, try to find that. And are x and y orthogonal? So I want you to find these things. So I will try to solve that, right? Are you able to find EY?
Is it 4?
Yeah, we will get into that. I will try to solve and then try to find out. So now I think in the expectation operations that we discussed about, right? Expectation operation is one of the operations that we can do on top of the random variables. So expectation operation, if we have like any kind of expression, we can it is a linear operator. Expectation is a linear operator. So expectation is a linear operator. So if we have some kind of expression where we have like a collection of x, y, z, likewise random variables, we can apply expectation operation to all those all the expression with that collection of random variables. So if it is like, if there's expectation, if we want to find expectation of ex plus y plus z, then it is going to be equal to ex plus ey plus ez. So when we consider this situation, we can apply the same concept. So y equals minus 6x plus 22. So if ey, I will take as e of minus 6x plus e of 22, right? So the value of the expectation value of 22 will be equal to the constant itself. So we will keep it as 22. So for the case where we have like minus 6 of ex, we have to take the constant out, and then we will remain with the ex e22. So ex has been given to us as 3. So minus 6 into 3 plus 22. Expectation of a constant is the constant itself. So we will remain with the 22 minus 18, which is 4. So yes, your answer is correct. Then uh, do you have the answer for the second question? Is there any correlation between these two signals?
It is 4 again. Am I right?
Sorry, I'm asking whether they are correlated or not.
Oh, the question was if they are correlated, what's the answer for EY? Is that the question? I thought.
No, no. Are they correlated? Are x and y correlated? I mean, first I asked about this value, but
Okay.
in the second and third questions, I'm asking whether they are correlated. And third one, whether they are orthogonal. So you can't find a value for that. You need to say yes or no, and you have to find it using the, the
They
equations
are
that we.
correlated, but not orthogonal.
So I will get into that, right? So how did you get into the answer? How did you get that answer?
Y equals minus 6x plus 22. The equation is linear, so I thought it's correlated. It to be orthogonal, it it it's supposed to be in an equal or a canceling out situation. So that's how I got it. I'm sorry. It's
I
a
mean, without
ballpark guess.
mathematical, calculations.
Yep. No
Uh,
mathematics. It's a ballpark guess.
so, you can mathematically show this. So, using that method, I think we can directly say whether these are correlated or orthogonal, those things. So, I think we can use the mathematical method of doing it. So I think we can, we cannot really, sometimes it's difficult to say by looking at the expression itself. Although in here, of course, we have a direct linear expression, but in situations we don't have that, then we can follow a certain mathematical steps to do that. So when we want to find the correlation, as I said before, we have to find this, we have to follow these expressions that we discussed earlier. Only these, using this, we have to define the correlatedness or uncorrelatedness or orthogonality. So we can find the ex ey, and we can see whether the product equals exy, right? Uh, if they are equal, then we can say it is uncorrelated, right? So that is the way of telling whether they are uncorrelated or not. right? That is the, I mean, that is one method of telling that. But yeah, you can use other you can use other methods, but it's better, I mean, it's one of the methods of doing mathematically is this one. So the mathematical way of proving the uncorrelated is showing that these values are similar like this. So exy value we can find um, separately, and then you can find exey values, and then you can try to find whether these things equal or not, right? So I think the another student has given 440, but I don't know what it means, right? So
That's right.
I'm not asking for a value, but I want
I
you to
don't know.
logically show whether these ex values are equaling or they are not equal, right? I'm not asking for a value here, but it's good to find the values. You need the values, but it is not the final answer. So in order to find the final answer, you need to find the expectation of this EXY. So for this case, we can denote EXY as X into Y. You can denote as minus 6X plus 22. So by solving this, you can say that this is equal to minus 6x squared plus 22. And then by taking the constants out, you can get this expression where we have again minus 6x ex squared plus 22. So we have been given as ex squared has been given as 11. So I will take as minus 6 into 11 plus 22, which is equal to 0. So this is the values, I think these are the values that maybe you have got. So this step is good, but it is not the answer, right? You need to calculate whether this is equal to EX-EY product. So EX is equal to 3 and EY we found earlier it is equal to 4, and this is equal to 12, and this EX-EY is not equal to EXY, right? And because of that we can say they are not correlated, sorry, they are correlated, right? This is not true, right? So if it is not true, then we can say that X and Y are correlated, right? This condition is valid for uncorrelated signals. So for uncorrelated signals, this should satisfy. But since it is not satisfying, we can say that X and Y are actually having some relationship between them and they are correlated. There's some kind of similarity between X and Y random variables. And then I asked about the orthogonality. EXY should equal to uh, it should equal to 0, right? So earlier we found that EXY value is equal to 0, which means that it is orthogonal. That means X and Y variables are orthogonal in this case. So for the answer for the third question is that yes, X and Y are orthogonal. So mainly the inner product is equal to 0. Inner product of X and Y equal to 0. So because of that, X and Y are considered as orthogonal. So because of that, we get the answer for third one is yes, right? The answer for the second question is no. So that is how the answers will be. Do you have any
Question,
questions?
ma'am. Yes, please, ma'am. Can you
Yes.
go back to where you solve EXY? Minus 6 into 11 plus 22.
This
Uh,
place.
yeah, um, 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 I'm having trouble how you got 0, if that's all right.
Okay. So minus 6 into EX squared, right? So
Yes.
22. Sorry. So in here, it should be actually in here, it should be x in here, right? So I have not multiplied the 22 with x. And in that case, if I'm going to take the expectation uh, of x, then it should be minus 6 into x squared is going to be 11, and here ex is going to be 3. So finally, I think it's going to be minus 66 plus again 66.
Yep, got it. Thank you very much.
So that is how that solvation will be done. Actually, I have not done the multiplication of 22 with x. However, like in here I have to consider the multiplication as minus 66, and then I need to consider the other section, which is again equal to 66. Anyway, finally I have got the final answer as 0, which is the one that I had wanted to find out. And then using that, I wanted to find out whether they are orthogonal and correlated. So do you have any questions so far?
Nope. Nope. Thank you.
Right. So then I will move forward. So I will discuss about uh, I will discuss about the next section uh, of this discussion, which is the section about the random processes. So we discussed so far about random variables and then multiple random cases. And now we are going to talk about random processes. We will ask like, what is the difference between all those situations? So I will try to brief those 3 situations using a table, and then I will try to uh, I will try to discuss about the random processes. So for the random variables, we had one random variable xo, one random variable y that we considered. So it could be like xo, some kind of a one random variable. Then we considered multiple random variable cases. When we have multiple random variables, we had to consider x, y. Likewise, we have like multiple, random variables. It could be going up to z, a, something like that. Could be other random variables that are in place, let's say x, y, z. There are multiple random variables that we are considering, and then based on all these x, y, z random variables, we get the we infer something about the random variables. So in the random variable case, we infer the behavior of the x random variable using the probability density functions. The probability density functions or probability mass functions, we inferred the probability of this random variable occurring. So we use the PDF value, PDF function to infer the behavior of the random variable. And then we also use the expectation operation to find the mean value or the mu value of the random variable. So if we take, for example, the random variable x, we found the random variable's average using this expectation operation. And that value we can find using integration of x into its PDF function, uh, and we integrate it over the x-axis. Apart from that, we define the general definition of the moment of the random variable, or the mth moment of the random variable. We denote that as x to the power m, and then expectation of that random variable of, if we take in this situation expectation of x to the power m, we denoted again using the integral x to the power m fxx dx, and then we denoted using this integration. By solving this integration, we can find this expectation operation, and we can do that for any value of m. We can find that for any value of m. So apart from that, we also discussed about the variance. The variance value, which we denote as expectation of x minus mu, and it's squared. So the squared of x minus mu squared is given as the variance of the random variable x. So variance gives us like what is the gap between the certain x value and its mean value, right? There's a mean value for the random variables. So once we take each and every value of the random variable, what is the distance gap between between that specific certain, random variable value with its mean value? And then we take the square value to take the positive value only, and understand what is the gap between the mean value and other values of the x. So that we denote again using another integration, which is x minus mu squared, and multiply with the PDF value, which is fxx, and we take the integration over the x. So this integration we take over the all the values that the x can take. So that is how we find the variance. So variance we also denote as sigma squared. And if the variance is denoted with respect to random variable x, we denote as sigma squared capital X. So when we take the uh, single random variable case, those are the things we discussed about. And then we discussed about the multiple random variable case. And for the multiple random variable case, we denoted this we have to denote this probability density function with respect to two random variables, and it could be x and y. Multiple random variable case can be having multiple random, more than two random variables. In our cases, we mostly talk about two random variables, x and y, and how the probability of that uh, of that probability uh, varies once we have both the x and y in place. So in that case, now the probability will vary based on both the x and y's behavior. So in that also, we use the expectation operation to find uh, behavior of the x and y variables. So in that case, we discussed about x and y, how the expectation of x and y, the product, the expectation of the product of the x and y changes. So the product of x and y is also denoted, or expectation of the product of x and y variables is also denoted by the correlation, or it is denoted as the correlation between these two random variables. The correlation we can denote again like integration, where we denote the uh, x and y, and we write the joint distribution function as the PDF function, and then we integrate over dy and dx. So in here we take the double integration over the dy and dx. So the correlation function is defined in this manner. apart from that, we define how the covariance is defined. The covariance is denoted as COV, and we denote it as x and x comma y, covariance x comma y. And then we have the its own definition, and we had the integration of the x and y with their means. Sorry, I mean the variation. Sorry, the variance. So I will denote first the expectation definition, and then I will denote the integration. So using expectations, we can uh, take the product between x minus mu x and y minus mu y, and the expectation of that will be equal to the covariance. This we can denote using integration as before, where we take this expression as the one where we take the integration. So the integration will be with respect to the joint uh, distribution function. We are talking about multiple random variables. When we are talking about multiple random variables, we have to put the joint PDF function in here all the time when we are doing the integration. So joint PDF function must be input here. And then we take the integration over all the values that the x and y can take. And apart from that, we also understood that by using the values of EXY, we can say what type of random variables are x and y. We can say whether the random variables x and y are correlated, or whether they are uncorrelated, uh, or whether they are orthogonal, or whether they are independent, right? So those things we understood. So I will write independent in here. We can find these properties of these random variables using the EXY product. The EXY will be equal to EXEY if it is independent. And for correlated also the same thing. However, like the inverse will not be same. So inverse will not be same if there are some dependencies between x and y. For orthogonal case, we have the inner product or this EXY value equal to 0. So we looked at that through certain examples. So now we have to, now we are looking to advance this further, which is by learning or by considering random processes. Random processes and the random variable case and multiple random variable case, you maybe you remember that we had a physical experiment, and those physical experiments had some outcomes, right? Different outcomes. So those outcomes in those situations came and they were mapped to certain values in the real axis. The random process, in the random process, the outcomes will be waveforms with respect to certain uh, with respect to a certain variable like time, for example, or space, right? These are the most common variables that we are mapping the output into in the random process case. So I will explain to you using some examples, but mainly the difference between random process and the other random variables is that in the random process we are mapping a certain outcome of a random experiment into a waveform. So the outcomes of the experiment will be a waveform along the time, let's say, right? The outcome will be obtained along a time, along number of time instances. So the outcome will be not a single number, it will be a sequence of numbers the outcome will be a sequence of values. The outcome will be a sequence of values. So for each outcome that can happen from in this experiment, where random outputs can be expected, right? We are conducting a certain experiment with random outcomes. Those random outcomes will uh, can be one outcome can be measured over sequence of time. The outcome will not be one value or one instance, but it is a collection of instances. There's a sequence of values that come as an outcome of one uh, as an outcome of this experiment. So I will explain to you the examples. Right. So one example is that the situation or the case of flipping a coin, right? Flipping a coin n times, flipping a coin n times. So in the random variable case, we consider flipping a coin uh, as an experiment, right? So in here, flipping a coin n times is the experiment. Flipping a coin n times is the experiment, and different outcomes can happen uh, in this experiment, right? So we consider if we consider a coin, we have heads and tails, and then uh, if we do this experiment one time, that means like we flip a coin for n times, right? So the output of that will be maybe heads first, tail, then heads, something like that. Let's say we do this experiment, I mean, we flip the coin for 3 times. So the outcome one will be heads, tails, heads. Then sometimes it will be heads, heads, and tails. Thirdly, it could be tails, tails, and heads. Likewise, it could generate multiple combinations of the coin flipping, right? Heads, tails, heads, 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 tails, 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 heads, and other combinations. So there could be some combinations that can happen. Uh, there could be different combinations that can occur at each time instance we are doing this experiment. For each time instance, for each we call that for each realization, we get a certain different output. So each of these different outputs that we can get from that experiment is known as realization. So this each different output that we get is known as realization. So uh, this we will say this is realization 1, this is realization 1, this is realization 2, this is 3, this is 4, likewise. So in our day-to-day lives, we are we are working with these kind of sequences of numbers or sequences, right? So most of the time we don't stop after getting one outcome. Most of the time our outcomes keep coming for a certain time duration or for an infinite time duration. So in that case, uh, we need these, I mean, we need the definitions of the random processes to identify how the outcome of these sequences or how the outcome of these kind of like sequence of out values will change uh, based on the random process. So another example, right? So this is a one example, the flipping a coin n times. It is a one example, and So this flipping a coin has now uh, so we have learned about discrete random variables and continuous random variables, right? So this flipping a coin n times can be uh, denoted using discrete random variables or continuous random variables, as you think. Is this I mean, is this experiment producing discrete random variables or continuous random variables? It is discrete, right? So thank you, Martin. So actually, this flipping a coin is a discrete process. I mean, that gives discrete outputs, countable outputs. Because of that, this process that gives different outputs, different realizations, is known as a discrete random process, right? So the flipping a coin process is a discrete random process. Discrete random process. So this discrete random process produces discrete, I mean, sequence of out values, discrete sequence of values. Apart from that, we can consider continuous random processes. So let's consider continuous random process, such as uh, we will consider the case where the where we consider where we consider uh, an experiment where we we uh, we keep recording some uh, I mean calls that come to our smartphone. So right, so receiving different uh, receiving different calls, di- receiving different calls from um, uh, receiving different calls uh, at a certain receiver, right? So at the receiver of a certain communication, we will receive different calls. So so let's consider that a person is calling or number of people are calling a certain, I mean, a certain receiver. So in that case, that experiment will, I mean, consist of different transmitters, and transmitters 1, 2, 3, 4 will transmit different signals. So those different signals that will be transmitted can be mapped as a uh, sequence of I mean values that will be received over time. So the values of the signal will be varying with the time. The amplitude of the signal will vary with the time. The amplitude will vary, let's say like this. So uh, the amplitude of the call will be varying like this at a certain time instance when a certain caller is calling call 1. Then call number 2 will be received again with respect to time, and then the amplitude of that call will be different to the one that we had earlier. Likewise, we will have another sequence of signal outputs which will be maybe different to what we had earlier, I mean in all the previous cases, and the amplitude of the signal will vary differently. The amplitude of the signal will vary differently each and every time a new call is coming, right? So the reason is the signals are random. So the signals are random, and although we try to send certain same signal, even if we try to send the same signal, because of the random noise that is affecting the communication, the amplitude of those signals will vary. That is very unique to that call. So in a so if we take noise is very random in all these cases. The noise that will affect this signal, the noise that will affect this first signal will not be the noise that is affecting the second signal. So the noise values will change. Because of that, the noise value is different in each of these instances, and because of that, the signals will change every time. So although we get the same message every time, the output amplitudes will be different due to other impacts such as noise, interference, those things. So in these cases, like if we try to analyze all the different calls that we got, we need to consider the different the we need to consider the probability density function, right? So I think that in order for us to analyze a certain random variable, we use probability density functions earlier, right? Probability density function is the one that we use to find out how the probability of a certain event occurring in the random variable case. Right? Probability density function is the one that we used. In the multiple random variable case also, we use probability density function to find out the probability of some event occurring. And there's two random variables in place. In the random process also, we need to consider a probability density function, right? In the random process, however, you have like multiple, I mean, values in the outcome. There are multiple values in the outcome, the sequence of values. So because of that, we will consider every value one by one, right? So, uh, so with respect to time, we will consider like one time instance, like time equal to 1 second. And then for the second variable waveform, time equal to 1 second. There also we will consider the amplitude. So in the fourth waveform, also I consider the time instance of 1 second. So by considering one value for the real for the random variable, one value, right? One value, I can identify what is the pattern followed by the amplitudes in that time instance. So I will try to draw this, but I don't know whether this will be like a straight line, but I want this to be a vertical line. So under time equals 1 second, I will take the amplitudes of all these waveforms and I will plot the probability density function of the amplitude, right? I will draw the probability density function of the amplitude. So amplitude at this time, I will denote as x1, right? Amplitude I will denote as x, right? X. And then amplitude at time t1, I will denote that as x1. So by considering the values of the amplitudes that I receive for uh, each of these waveforms, I can find the probability density function of this x1. And then that probability density function will most probably be following a certain random, uh, uh, I mean, distribution function. So in wireless communications, the amplitude of the signals are said to vary and follow the Rayleigh distribution. So therefore, for each time instance, the amplitude of these waveforms will follow probability density function, which is the Rayleigh distribution function. Rayleigh distribution function. So the probability of the amplitude, of the signal can be found using the Rayleigh distribution function. So this data can be important when we are trying to find the probability of an amplitude occurring at a certain time instance. So when we take another time instance, let's say time t equals 2 seconds for all the waveforms, then there also we will observe that the same distribution function is used to denote the probability density function of the amplitudes. So that is the kind of uh, standard distribution function we use in our wireless communications to uh, to model the amplitude variation of a signal. So amplitude of a signal in a wireless communication, transmission, the wireless communication, uh, the amplitude of the signal is denoted to vary according to the Rayleigh distribution function in most cases, right? It could be other distribution functions as well. Most of the time when there's like non-line of sight communication, then we use the Rayleigh distribution function. So the Rayleigh distribution function can be used to model the amplitudes of the signal at a certain time instance, right? So this PDF that we draw is for a certain time instance. This is for time equals 2 seconds. This is for the time equals 1 second. So this PDF value is there defined for one time instance only, right? And for each time instance, we can define that the probability of the amplitude varying is also according to the Rayleigh distribution function, right? For each time instance, we have to define separately the PDF function, right? So that is how we can define the PDFs of a random process, right? PDF of a random process has to be defined for each random variable in this axis, and that is the PDF of that specific time instance or specific space instance. So it is defined for the specific time instance in this case. So do you have any questions? So I think maybe these things are maybe new to you. In that case, like I want you to go through these things when you have some free time, and then you can think about those things in your own space, and then you can maybe try to understand the whole concepts much better. So I think I will ask you to refer these things in your free time as well. So I think some concepts are very kind of statistical, and therefore might not be able to, might not be maybe very clear at the first instance of maybe learning. However, like you can learn on your own in your free time as well. So in this case, we actually consider about this continuous random process. So, so this continuous random process has values as the output for each and every time instance for the certain time duration that is considered. So, um, with all this, we actually considered um, we actually considered the case where we have the continuous random variable and how we can define the PDF of the random uh, uh, for a single random variable and for a specific point in the for a specific random variable, let's say time equals 1 second, we can define the probability density functions. And by defining the probability density function for each of these realizations, right? So we call these different outcomes as realizations. So each of these waveforms we call as realizations, right? I think I explained to you about realizations in the head flipping case, the flipping case. In here also we have the realization 1, realization 2. Likewise, we have up to realization n times. We can have number of realizations um, from the same random process, and all these realizations um, all this realization will constitute of something called ensemble. So before going that, I will explain to you about another parameter that we need to consider. So as I said before, each of these points can be denoted using a probability density function, right? So after you have decided the probability density function for these time instances, we can find the average of of the uh, of the of the random variable that is at the time equals 1. So the average value, you can find uh, expectation of the uh, variable at x1. X1 is the amplitude of the signal at time equals 1 second, right? Amplitude amplitude of the signal at t equals 1 second, I denote as x1. So amplitude of the signal at that 1 second time instance, I can count or I can calculate for all the different realizations. There are three different realizations. Let's assume there are three different realizations. For these three realizations, I will compute the amplitude. And then by using the distribution it follows, I can denote its distribution. And then in order for me to find the expectation, I will take the average of all those amplitudes in these three realizations. If there are three realizations, I will take the average of the amplitude. The average of that amplitude I can find by expectation operation on the amplitude that I get at time instance 1 second, that I denote as x1. So expectation of x1 will be the average, right? So the average value I can denote again using a integral, which is x1, right? So what is the average value here? How can you determine the average value using integration? It's going to be x1 multiplied with its probability density function, right? X1's probability density function. X1 has its own probability density function, right? The probability density function is here. This is the probability density function of x1. I will denote it here just to show it's for x1. Then this probability density function should be applied here in this integral. And then we have to take the integration. And the average value of the x1 values of x1, average value of x1 comes by multiplying the random variable with its probability density function. Probability density function is a Rayleigh distribution function, and we can find the average amplitude at x1, right? So that is the kind of idea about the expectation operation that that is used to uh, kind of measure the average value of the amplitude that you can get at a certain time instance, right? Uh, so we that is the kind of the procedure we followed for the other random variables and multiple random variables as well. We first define the probability density function of the random variable. Then we found the mean value of the random variable. So for the other things also same thing. Like for the joint random variable case, we had 2 or 3 random variables. If we take 2 random variables into consideration, we found the expected value of the probability density function. Sorry, we found the average value of the xy values. Right? We took the multiplication of x and y and we found the expectation value. In here, the random variable is actually the uh, uh, the uh, the amplitudes that we can take at x equals time 1 second, right? So for this random variable, we can define a probability density function. The probability density function is defined like this, where the random variable is x1, right? Whatever the amplitude that we can define, that we can observe at time equals 1 is denoted as x1. And the probability associated with x1 is the is given using this probability density function. So the random variable here is x1 therefore. The random variable here at one time instance is x1. So the corresponding probability density function is fx1 and inside brackets simple x. If you want to find the expectation operation, we need to multiply the random variable with its probability density function. And we have to integrate over the dx. So this is just one random variable of this sequence. There are infinite number of random variables in this sequence. As you can see, time equals 1 second is just one random variable of this sequence. This sequence is composed of a number of random variables. So we can define the expectation for each of those random variables separately. So if the probability density function is same for each of those random variables, then we actually have a special situation uh, and we call that process as a stationary process. We will get to that in the maybe in the next class as well. I will just explain here because we have that happening here. So I explained to you that now in the time equals 1 second, we have a Rayleigh distribution which can be used to denote the probability density function of the random variable x equals 1, x1. So when we take the probability density function of x2, even in there we have the same probability density function. So if we have the same probability density function for each of the random variables, x1, x2, up to x some let's say xn, we have the same probability density function for all these random variables, then we call such kind of random processes that produce such kind of outputs. We call such kind of processes as stationary random processes, where the probability density functions are equal uh, for all the random variables. So in this case, if the probability density function is equal for all the random variables, then we call that random process as stationary random process. So stationary random processes have same probability density function at each random variable value, right? So random variable 1, random variable 2, random variable n, they will all have same probability density function, same function to denote their probability of occurring. So if the probability density functions are equal, then we call that process a stationary random process. So that I think I will explain in the next class. So do you have any questions? Uh, if you have any questions, you can let me know. Okay, lecture note. I will try to upload the lecture note, right? I will try to upload the lecture note. Maybe this sketch I will try to upload. Is it okay? Apart from that, I have also I have the lab assignment that I'm going to give you, and I'm going to explain to you now about that. So I will upload a lab assignment for you to conduct or do. I want to know, like, do you want to do the lab assignments as a group activity, or you want to do it individually? I was initially thinking to do it group wise. Uh, is anybody here in this meeting? Can you explain to me whether you like to do this group wise or individual? Gayan, are you here?
Yeah, I'm here. I didn't say anything because I don't want to be unfair to others. Because for me personally, I would say it'll be easier if I can do it by
On your
myself.
own. Hmm.
Uh,
Yeah. So, I mean, I will give the option like for you to do either in individual or group wise. Then anybody, I mean, you can do either like group wise or individual. But I think sometimes, I mean, I don't know. Maybe like normally, um, there are people who like to do individual, um, and then, however, like the marks will depend on the quality of the output anyway, and like whether it's group wise or single individual contribution, the same way of marking will be done. So I don't know whether it's going to be unfair for the individual students, or I mean, I don't know, like, because even sometimes, even if you do like group projects, sometimes the quality is not that as expected.
yeah, because you know how it works.
Maybe yeah, you can decide that. So I mean, I will anyway allow you to work in pairs, mainly because I think there are some students who are not that familiar with MATLAB. And if you want to learn MATLAB from your partner, work with them, and then you want to understand that by discussing with the others, then you can do it as a group activity. I have no objections. So I think like during my MSc, when I was doing, I was also having the kind of signal processing module to do, and then we had the lab assignments, and we had group assignments. And in that case, actually, I don't know, I think I worked, I'm kind of okay with the group as well. But there are students who did individually as well. So there was no much of a difference between doing individual and group, because uh, there was not much of a, because the individual person anyway, they also try to obtain the same level of performance. They were also kind of working with us. I mean, so because of that, I think you can decide whether you want to do group wise or not. Anyway, like I will upload the assignment in the LMS. So you want to you have to first specify whether you are working like a group, and if it is working as a group, then you need to define your group members there. I will upload an Excel sheet for you to upload the member details. So with regard to the like assignment, the assignment will be as in the screen. I hope you can see that. The assignment is something that I have already like explained to you about, like how we can use a signal analyzer. So I think it is something that I think we have done like a little bit. So in here, you have to import a like audio signal of your choice. Can be some kind of signal, but I prefer it if you have a signal with a lot of like high frequencies, low frequencies, and middle frequencies, or band pass frequencies. So I prefer if you select maybe a song or some kind of a music file that has different frequency components. So you need to like convert that signal into a like a like a type that you can process in the MATLAB. So first you need to download the song, and then you need to convert it into a MATLAB file or MAT file. So after that, you have to import that audio signal into the signal analyzer app. Then use the analyzer app to visualize the time domain and frequency domain waveforms. After that, you can use a low pass filter and high pass filter, band pass filters to extract specific frequency components of the audio signal. After that, you can combine the filtered signals appropriately, and you can see, you can combine the filter signals, and then, you have to consider all the possible combinations, low pass, high pass, and then low pass, band pass, maybe two by two you can consider. And maybe after that, you can consider all the filter signals together. So you can mention the maybe combinations that you considered. And then after that, you have to choose the best combination that gives the best output signal that you prefer. So you can decide it on your own. So you can choose the one that you like the best, and you can present that. So you need to do the signal analyzing part in the signal analyze app. After that, the filtered signals you can again you can try to evaluate their sound signal using the MATLAB code. And then you have to show the filtered signals in the signal analyzer app, the window. And then you can save it as signal analyzer app has a different format like MLX or MLD, something similar, and you need to save that file in that format so that I can open it and I can view it. And then you have to create a small report mentioning the procedure that you used. Just it doesn't need to be very lengthy. You can use the procedure you have used to obtain the filter signals, and you can include a table that include the simulation parameters that you utilized to um, generate the filter signals. So one person is asking this question, Murad. We apply the filters mathematically or using MATLAB modules or functions. So in Signal Analyzer app, you have Analyzer tab. In the analyzer, you can select like you can select high pass, band pass, low pass. Those functions are already available there. You don't need to code it. You don't need to code it. So then thirdly, discussion. So you can compare the characteristics of the original signal and the composite signals, and you can explain the difference between the filtered signals and the original signal. After that, in the appendix, you can include the sample codes that you use to observe the audio signals, and you can use some comments to explain the code. And then links. You can include a link to the MATLAB files that I can access, and then I can download and maybe open in my own MATLAB window. So you can include a link to your file as you wish, a working link. And then also I want a video demonstration of the simulation. It could be 1 minute video, right? Just 1 minute, 2 minute video, just explaining how you got the signals and how you filtered those signals. Right, that video demonstration also is necessary. The video demo and the report I need. So those are the things I want you to do. So do you have any questions about the lab assignment?
When is the deadline for this?
Well, actually, no, are you, my idea is that I will define the deadline as January 27, which is in 2 months, I think. Because it is the last day of my lecture, right? Until that point, you can submit the assignments. I will keep giving some assignments in the next classes. So all the reports must be submitted by that time. Is it okay for you?
Yeah, thank you.
Okay, so do you have other questions? I will upload this, and I will also upload the grouping, Excel sheet to include your group members' details. So if you want to work in groups, please add your member details in there. You can work with them and you can submit the assignments. So the deadline I will mention there itself in the LMS. So that is it for today's class. I mean,
One
content
question, ma'am.
wise.
That's all right.
Yes. Yeah.
Can
Yeah.
you
Please, Sabine.
go down a bit in the document, please? In the discussion part,
Yes.
what kind of a discussion that you're expecting?
I
Please.
want to like maybe explain like how the original signal has been changed, like in terms of maybe the the frequency, the power or power spectral density. I haven't told that now actually, but you can discuss about the frequency components in the final composite signal and the frequency components in the original signal. Uh, now once we have filtered the signal, some frequency components do not appear there. So maybe you can mention like about, I mean, you can compare. So I will put in here maybe the you need to compare the original signal and filtered signals. No, filtered signals. Filtered signals. Yeah. You just compare the original signal and the filtered signals only, not the composite signals. Composite means you mix two filtered signals that you have filtered. Rather than comparing with the composite signals, you can compare with the original and the filtered signals. So in that case, like original and the low pass filtered signal, original and the high pass, original and the low pass, band pass. So you just can mention how the amplitudes of the signal has changed based on the filter applied. Is it clear to you?
Yes, ma'am. Thank you. I was writing it down. I'm sorry.
No
Thank
problem.
you very much.
Okay, thank you so much. So I will stop the recording.